and then briefly talk about the amazing tool that is diffusion models and sort of deep generative networks for generating images yourself. And Brandon will describe how you can do that using existing tools. Right. So a camera, whether it's a big DSLR or the simple stuff you have in your smartphone, consists of three components. You have the optics, you have the sensors and the filter array, what turns light into a digital signal, and then you have the image processing pipeline, which is where the magic happens, where we turn raw digital signals into the beautiful images you'd like to share online. We're just going to briefly run through how each of these work, and then how you can implement some of this image processing yourself using Python and existing online tools. So let's start off with a digital sensor. So this is just a sensor that's going to record photons that hit it. And then let's assume that we have a scene located some distance fairly far away from the sensor. We are going to have light that's emitted from the scene, and this light's going to propagate, and the light from that pixel of the scene, that location of the scene, the very top of the tree, is going to propagate, and it's going to make its way to the digital sensor. But it's going to propagate in all directions. So it's also going to propagate all the way to the bottom of the sensor. And similarly, the light here is going to propagate out. It's going to reach the sensor at the bottom. But it's going to reach the top of the sensor as well. And so if you have a sensor like this and a scene that looks like this, and you turn the sensor on, capture an image, you're going to get something that looks like this, complete garbage. Essentially everything's mixed, blurred, there's really no meaningful information here. And the reason for this is that each of these pixels on the sensor is capturing light from the entire scene, and so you need some way to restrict what it is you capture. Make sure this sensor in the pixel, this pixel in the sensor needs to correspond to some physical location in the scene. And one easy way to do that is with a pinhole. Rather than just having the sensor directly see the tree, we're going to instead put a barrier between them, introduce a pinhole, and now with this barrier, light's going to propagate out in all directions. But the vast majority of it's going to hit this barrier and be blocked, and only a small fraction of it's going to make its way through and hit the sensor. And now we have essentially mapped this spatial location. That the top of the tree is only recorded on the very bottom of the digital sensor. And similarly, now the very bottom of the tree is only recorded to the top of the sensor. And so what we end up recording here is just a copy of the real world object that's flipped and inverted. There's sort of one-to-one correspondence between a spatial location on the sensor, spatial location in the scene. Now, so this is what's called a pinhole camera, and it produces nice sharp images, and it's sort of really useful for understanding how a camera works. But note that we had a ton of light that propagated to this diaphragm, to this camera. And the vast majority of it was blocked. We recorded very little of the light that actually made it to the aperture. Now we can improve this. We can capture more light. By making a larger aperture. But this is going to blur things out. So if we have a larger aperture, now we're capturing light at all these angles. But now this pixel, rather than just recording a single pixel from the scene, is going to capture light from a whole region. It's going to produce a blurry image. And so you have this tension. The smaller you make the pinhole, the sharper your image is going to be. But if you make it really, on the other hand, you're going to capture less and less light. And a way around that is optics. And so by introducing a lens, which a lens, what a lens does is it bends light. Essentially we now essentially have a pinhole camera, but our pinhole camera captures light that hit any region on the lens and maps it to a single pixel. And so now we essentially get the best of both worlds. We're capturing a ton of light. We're capturing any light that hits the lens, but we're still getting nice one-to-one spatial correspondence. And so this is, that's the operating principles of a camera, or of the optics of a camera. And now, we've mapped light onto the sensor. Let's turn it into an image. Let's record it. So, we've mapped light onto the sensor, and when the exposure begins, we can think of our sensors as an array of photon buckets. They count, they count the number of photons that hit them, and they effectively, store how many photons have I seen, and they do this, from when you press the shutter, when you press the shutter until the shutter closes. You open up, start exposing, and then close the shutter. Each of these pixels has a makeup that looks something like this. You have a color filter, you have a photosite, which turns photons into electrons, and then something that stores electrons, something that lets you count the number of electrons.
Number of photons. Everyone TP towards A though. We're gonna book it A after we send it.
Hit the sensor. And the goal of the color filter is essentially to block light that isn't blue, to block light that isn't green, and to block light that isn't red. And if you put, so after you block the light that is, is blue, or that blocks all the light except the blue light, you now have this photosite, which again, takes photons, converts them to electrons, which you now, store and measure. And so, that's, how one pixel works, but you don't just have one pixel, you have, say, 1 million pixels. And each of these pixels is going to be colored, covered by a blue filter, a green filter, a red filter. And that's going to let you, capture red, green, and blue information about the scene at once. So one might wonder, why do we have, 2 green filters, 1 blue filter, and 1 red filter? The goal here for most, for many of the applications we're interested in is to, capture images that we're then going to display to human users. Human eyes are far more sensitive to green light, and so it's more important to get a good measurement of the blue light. Let's measure that twice, and we don't need to be quite as careful with the blue and the red. And that finally leads us to the image processing pipeline. And so, we formed an image, we've mapped it onto the sensor, we've, recorded the number of photons, and now, we can think of what's, captured, behind each of those Bayer filters as, essentially we have 3 grayscale images, each corresponding to a different color channel. So we have the red channel, the green channel, and the blue channel. And so if we have a 1 megapixel image, it's like 1 megapixel RGB image, it's like we have one 1 megapixel red image, one 1 megapixel green image, one megapixel blue image. And the way here is that we can understand digital images is just an n by n array of numbers. So each pixel location, pixel location there, tells you, here's how bright, here's how red that pixel is, here's how bright that pixel is, here's how red this pixel is, here's how red this pixel is, and green and blue, etc. And essentially, with that understanding that images are just arrays or a set of 3 arrays, we can now do all sorts of manipulations and enable Photoshop, enable image editing, enable all these sorts of manipulations you might want to do. And so, let's think of our image as, we have this n by n by 3 array, and we're going to call that X. And if we want to darken that image, we're just going to, take each of those values, which says how bright, each pixel is, subtract a number. If we want to make it, lower contrast, we divide it. If we want to reduce the contrast, in some bizarre way, we can do something like that. We can invert it by, flipping the sign. We can lighten it by raising it, by a scalar or a multiplier. And we can do so non-linearly as well. And so, with that, I don't know a good way to show this and then go there at the same time. So yeah, so go to github.com, intelligent sensing, Technica, I guess it's 2021, but or sorry, rather copy that and go to collab.research.google.com. Let's see if there's a way to. All right. So all right. So for those of you who have this open, you can click files and then the upload icon. And then choose 2 files of yours that you'd like to upload. And now with that, so the first bit of code here is taking a file name, irib, and now we're going to read it in twice. We're going to either read it in once as a color image and once as a, oh, and am I not sharing? Yeah. No. Sorry. So to get there, go to collab.research.google.com, and then you'll then put that in chat. All right. So at this point, you've opened up an image and you've displayed a color image. And then we're also displaying the grayscale version. And now if you call the command cv.canny, these parameters, that will run what's called an edge detection algorithm, which is going to take this image that looks like this and compute all its edges. And now at this point, we can choose a rectangle. So we're going to choose 4 corners. So this is essentially chooses 4 corners of the image. So 50, 50, and, or 50, 290, 450, 50, and 450, 290. And then we're going to run this algorithm. It's called grab cut, which is essentially going to take the edges we had and try to trace a line around the image that follows the edges as much as possible while grabbing as much as the image as possible. And so if you run that, you'll get a mask. And then if you multiply the image by the mask, you see that it looks like this. Essentially, it's found, given 4 corners, it's found, well, here's a region that I can trace, trace edges around, and essentially, the sort of the snap tool in Photoshop. This is what's, going on under the hood. And now let's take a different image and resize it to be the same size as the first one. And now you can get an image that looks like this. There's your second image. And we're now going to multiply it by 1 minus the mask. So, the mask is a array of 1s and 0s. And so, where there's a mask, you keep the pixel. Where there wasn't a mask or where the mask was 0, you get rid of the pixel values. And now this mask is just the opposite. So essentially anywhere the Erie building was before, we've now set to black. And anywhere the cropped Erie image was black, we use our Hubble image. Now we just add these two together and voila, we have this, Erie in space image. And this is, sort of, a lot of what's going on under the hood in sort of modern Photoshop software, more advanced versions of this. And now I'm going to turn it over to Brandon, who's going to talk about sort of what's going to show up in the next generation of Photoshop and how you can already play around with it yourself using online tools. And I guess while I do this, it would be, while Brandon talks about this, it would be great if you can go to openai.com/DALI2. And if you'd like, you can sign up and create an account. And we'll come back to this later. All right. Oh, yeah. Not sure I'm host. Okay, cool. So where are you? Oh, there we go. Yeah. Just wanted to let.
Okay. I can give you that permission. Do it on my
So Brandon's going to describe the inner workings of how this works. But so DALI 2 has just been enabled so that anyone can create up to 50 DALI 2 images themselves using their compute. Brandon's going to explain how this method works. But So this is, pretty amazing software that lets you, type in your own prompt and, generate various, images. And, earlier in the day, I was playing around, with photos of my own cat. You can upload this, start here, and generate, just about anything you like. So very fun. Highly recommend you try it out. Cool. Good to go, Brandon. Oh, you're just going to do the presentation from you, or? Okay. Cool.
Yeah, no, just turn it on.
So what Professor Metzler just described was how people formulate images, capture images physically. And I'm going to discuss some of the latest cutting edge technologies and how people manipulate images. And specifically, they will be generating images, not physically, but digitally through text. And just so one example is, say you give it a prompt. I'm not sure if you can read it, but vibrant portrait painting of Salvador Dali with a robotic half face. And this is what that software that Chris just showed generated. And then you have a second prompt that reads, Shiba Inu wearing a red and black turtleneck. And then the third prompt is a close-up of a hand palm with leaves growing from it. And then you have three other examples. The second one is my favorite, a propaganda poster depicting a cat dressed as French Emperor Napoleon holding a piece of cheese. So all of these pictures were generated just from this text alone. And you can, as you already saw, you can enter any text of your own, and then the network is going to generate some very photorealistic, high quality picture. But how does that work actually in the under the hood? So you would first need this so-called text encoder, which is a neural network that takes in a long text, and then it's going to encode it into this long vector that's called the text embedding. And you want this text embedding to capture the meaning of this text in the form that the neural network can read. So you want to basically translate this English word into some, abstract latent word. And then you want that that embedding to match with something that you also can extract from the image. So you have your text description describing that image. So you can have two networks that separately encodes the text and the image, and you want their encoded embedding to be consistent with each other. And if you can do that with some training that we won't get into the details, you are confident that your text encoder can reliably translate this text description into something that the machine can read and interpret. So with that, let's take that text embedding and then that text encoder is already trained. So you can give it a new text and it's able to generate new images that fits your text description. And you might be wondering, why don't we use that image encoder in the first place? Well, you want to be able to generate a diverse set of possible images that is consistent with the same text description. And this decoder is able to generate basically an infinite number of images that based on the same text input. And the specific details about this decoder is very interesting because it's not directly mapping this feature latent embedding to an image. It's actually doing this thing called denoising diffusion. So basically, the decoder is going to produce a complete noise garbage image. And then it's going to gradually remove the noise from that image. And then then after several iterations, it's going to produce this that final clean image. And the text embedding comes into play during this denoising process. So you can imagine on a high level, your text embedding is biasing this denoiser to produce something that fits your text description. And this is like what in an animation, what this denoising procedure looks like. So you start from complete noise and then you gradually obtain something very realistic. And then, yeah. And then once you have that sort of network, you can apply it to beyond just generating some fancy image with the text. You can input 2 different sentences and interpolate their extracted embedding. And that interpolated embedding can be used to generate new images. Like, you have, from the left, you have like a photo of a Victorian house, and then you gradually interpolate it to a modern house. And then you have a photo of an adult lion, and then that morphs into a lion cub. And then the third one is a winter landscape morphed into the fall landscape. So the encoded embedding of the text can be interpolated in their very strange latent space, which is pretty amazing because you can't arbitrarily just interpolate English words, but you can do that smooth interpolation in that sort of extracted latent space. And then you have another application with that. So now that you basically have a very strong image generator that can generate very realistic images, now you can leverage its power to generate like very reasonable, plausible images, but you mask it out. So you have this region that you want to mask out, just like what we covered in the previous section. So you just want this network to produce something that's realistic in the region outside of the mask. And because the network has been strongly biased towards generating very realistic images, so even though it's only being supervised by regions outside of the mask, it's able to basically interpolate or hallucinate the region inside the region. And then, lastly, you can try your own prompts. This is the ones that I tried earlier today. A high quality photo of a dog riding a bicycle, and then you can change the prompt to the dog riding a bicycle with friends. So you have human friends and dog friends. And then the third one I tried was like a funny photo of a horse at Times Square drinking milk. I did not expect this to work, but it did. So now it's time for you to have some fun with the prompt yourself in OpenAI's website.
All right, so thank you all for being here. Like they both said, feel free to play around with OpenAI to do some of these things that Brandon was just showing you. Thank you all for coming. The workshop's gonna end in like 2 minutes. So yeah, if you want to stay and play around for 2 minutes, feel free to do so. Otherwise, please make your way out as soon as possible so we can get ready for the next workshop. And yeah, just thank you. Can we get a round of applause for our 2 workshop hosts? And yeah. Thank you guys so much.